Hey guys, today we'll be talking about the convergence of a series, and the series that we are talking about today is this. Oh, this does not look that good. Let me erase this. Anyway, this is the series that we are concerned with. So to start off, the a rule of thumb for a series like this would be to use ratio test. Why? Because we have exponents, power n to the power n, and we have factorials. So in cases like this one, it's better if you use the ratio test because it makes things easier and things eventually cancel out. So the ratio test is limit n tends to infinity and an plus 1 over an. And if the solution to this is equal to 1, then the thing fails, the test fails. If it is less than 1, then it is convergent. I like to write converge, the short form of convergent as CVGT. And if it is greater than 1, then it is divergent, DVGT. Okay, so that's the basic ratio test, what ratio test tells us. So yeah, let's go. So yeah, so limit n tends to infinity. So an plus 1 in this case would be n plus 1 to the power n plus 1, since this is an, and for an plus 1 you would just add plus 1 to the nth term, and for this it would be n plus 1 factorial, right? Times, now we are talking about an, times n factorial by n to the power n. How did I get this? Because we had this n to the power n by n factorial, and when we reciprocate it, then we get this thing. So I just skipped one step right over there. So let's just do this. Yeah. So now what we have is limit n tends to infinity as it is, n plus 1 to the power n times n plus 1. I used laws of indices for this one, over n plus 1 times n factorial. Again, let's say we have 3 factorial, then that can be written as 3 times 2 factorial. If we have 4 factorial, then we can write it as 4 times 3 factorial. So what I'm saying is n factorial can be written as n times n minus 1 factorial. That's the same concept I used right over here. I hope that is clear to you. Okay, times n factorial over n times n. So this cancels this and this cancels this, right? So what we are left with is limit n tends to infinity n plus 1 over n. We can get rid of the absolute sign because n starts at 1, so they're all going to be positive numbers. So yeah, we can get rid of that. So this can also be written as n plus 1 over n to the whole power n, since both the numerator and denominator have the same power. So you can split the denominator, and we would have 1 plus 1 over n to the power infinity, to the power n. And since, if you now input the value, then this will be 0, as anything divided by infinity would be 0. So we would have this, and this is indeterminate. We don't know what that is, so we need to do something because this is not helping us get an answer. So let's erase this. Now we need to think better. What do we do? Let's see. What if we do this? We know that if y is equal to e to the power l n y, this is a concept I hope you guys know, right? Like a is equal to e to the power l n a. So this is a property of logarithm. I hope you've discussed that in your classes. It's not very difficult to prove. So if you just go one step backwards, then what you'll have is ln a is equal to ln a, because let's say if ln y is equal to c, then what you can write it as is y is equal to e to the power c. So yeah, this is the same concept over here and here. So, and the reason I'm taking help of exponent, the Euler's number and logarithm is because e is continuous throughout, and one of the properties that you guys have probably have discussed in your earlier classes is if you have a function that is that limits that exist in limit n tends to infinity and this, then you can take this outside. So what I'm saying is, for example, if you have this f of x to the power g of x, and if f of x exists in the limit of g of x, then you can write this thing as f of x limit n tends to infinity g of x. I will be using that concept right here. So is equal to, so since e is continuous everywhere, I can write this as this. I just took the power and brought it in front. That's another property of logarithm. So now, what do I do? E to the power limit n tends to infinity n times ln n 1 plus 1 over n. So what I can do is, I guess, this. And when the n goes to the numerator, then we get whatever we had. But the reason I'm doing this is because now, if you were to insert the value of infinity here, we would have 0 over 0, since ln1 is equal to 0, right? Yep, ln1 is equal to 0. So now we are in this format. And now what we can do is you can use the L'Hopital's rule. So since this is in 0 over 0 form, we use the L'Hopital's rule. And by now, I'm sure you must have already discussed this, so I'm not going to go through the details. If you use L'Hopital's rule for this, then you get to the thing. The answer is e to the power 1. It's very simple, I'm sure you'll be able to do it, and is equal to e. Now, is e greater than 1? Yes, the numeric value of e is greater than 1, and therefore ratio test tells us that the series diverges. Therefore, now we know that this thing does not converge. Yep, the only trick or the thing that you have to be mindful of is using the concept of E and ln logarithm, changing this to this. That's all. The rest, I think, is pretty easy. So I hope you learned how to do this, guys, and hope to see you in my next video. Thank you.